Predicted topics for Paper 2, AQA A Level Chemistry Exam 2024, Part 1. This is for physical chemistry topics, and there is another video for organic chemistry topics. Topic 1, which is very common in your exam, and I would expect that it will show up in your exam this year as well, is the Arrhenius equation. So in the exam, they're going to provide you with the equation, so you don't have to memorize it, but you need to know the different terms within the equation and their unit. So K here is the rate constant, and A is the Arrhenius constant, which is going to be provided to you. And then EA is the activation energy. When you use the equation, the activation energy has to be in joule, not in kilojoule. And then R is the gas constant. This is going to be provided to you as well. And finally, T is the temperature in Kelvin. Remember that this part here determines the probability of successful collision in a reaction. So if the activation energy increases, that means this value will be decreased and the K or the rate constant will decrease, because increase in the activation energy means a decrease in the rate. And then also the temperature. If the temperature increases, that means this value of this part is going to be higher value, which means the K will increase. So we know that increasing temperature increases the rate of the reaction. Sometimes they give you all the different variables and ask you to calculate, for example, the temperature when the rate equals a certain point, or ask you to calculate the activation energy. So you need to do the normal logarithm for your equation. If they give you this equation, they're not going to give you this equation. So you need to know this equation or how to derive it from the first one. So ln K equals minus EA over R times 1 over T plus ln A. And then remember that now this is a linear equation. So you have y here, which is the ln k, and then mx, the m, which is the gradient, is minus ea over r. And then the x here is 1 over t. And then the p, which is the y-intercept, is the ln a. They can give you, sometimes they give you this graph, and they ask you, for example, to calculate the activation energy. In this case, you need just to calculate the gradient or find the gradient of the line, and then the gradient will equal minus EA over R, the R, which is the gas constant. This is going to be provided to you in the exam. And finally, sometimes they give you the equation in this form. You don't need to learn this or memorize it, because if they ask you a question about this, they're going to provide you with this equation. This is a change to different cases with or two different rate constants with two different temperatures, and they could give you the two different temperatures and ask you to calculate the and the two different rate and ask you to calculate the activation energy. You just need to rearrange your equation basically. The second topic, which is very common and I expect it to be in your exam as well, is reversible reaction and position of equilibrium and equilibrium constant. Remember that this is a reversible reaction, and the equilibrium constant is always calculated as the product of the concentration of your products, each of them raised to the power of their moles. You could have more than two products, so it depends on how many products you have, whether it's 1, 2, 3, or whatever, it doesn't matter. Just multiply the concentration of each raised to the power of their number of their moles divided by the products of the concentrations of reactants raised to the power of their moles as well. In your reaction, in your question, they can either provide you with the concentrations of the different reactants and products and ask you to do the calculation. But most of the time, this is not going to be the case. They're going to either give you the number of moles of one of the reactants or products and the initial moles at the beginning of the reaction of the reactant, and then ask you to find the moles of all of the different products and at equilibrium, and the reactant at equilibrium, and they're going to give you the volume as well, so you can calculate the concentration of all reactants and products at equilibrium, and then you can use this equation. Remember that the unit of Kc will differ from every time. That will depend on what powers did we use here in our calculations. Remember, the factors affecting the position of equilibrium are temperature. Temperature will depend on which direction is exothermic, which one is endothermic. So increasing temperature will push the position of the equilibrium toward the endothermic reaction. The concentration, this is for solutions only, and of course, increasing concentration of reactants will push the position towards products and vice versa. And then pressure for gases, increasing the pressure will push the position of the equilibrium towards the side which has lower number of moles. And finally, the use of a catalyst. A catalyst will speed up the reaction in order to get to the equilibrium faster, but it will increase the rate of both the forward and the reverse reaction, so it doesn't affect the position of equilibrium because of the both of them will be increased at the exact same rate. So let's practice. If we have something like this reversible reaction, two hydrogen iodides give you hydrogen and iodine. Remember, the Kc here will equal the concentration of hydrogen times the concentration of iodine divided by the concentration of hydrogen iodide squared. If they give you the initial mole of hydrogen iodide in this reaction, and then they gave you the number of moles of hydrogen iodides at equilibrium, and then they ask you to calculate the Kc, how would you do that? Then first you need to calculate the number of moles of the hydrogen and iodine at equilibrium. Remember, from this balanced equation, you can see that 1 mole of hydrogen and 1 mole of iodine are produced when 2 moles of hydrogen iodide reacts. So now you need to find how many moles of hydrogen iodide have reacted at equilibrium. So if they give you the moles at equilibrium, then the initial moles minus the number of moles at equilibrium will equal the number of moles of hydrogen iodide that have actually reacted. And then half of that value will be the number of moles of hydrogen, and also will equal the number of moles of iodine at equilibrium. For example, if the initial moles were 2 and moles at equilibrium 0.8, then that means 2 minus 0.8 is 1.2, and half of this value is going to be the moles of hydrogen at equilibrium, and also same for iodine. What if they give you the initial moles of the hydrogen iodide and then they give you the moles of one of the products? Then again, you can use the same, because the number of moles of hydrogen iodide that reacted will be double this value, so 2y. So Z, which is the initial moles, minus 2y will equal the moles of hydrogen iodide at equilibrium. And of course, because iodine, 1 mole of iodine and 1 mole of hydrogen will be reduced, so we're going to have the exact same number of moles for iodine. Then if you have the volume of your solution, and mostly will be given to you in centimeter cube, then you can calculate the moles over the volume in decimeter cube. Don't forget that you need to change it or convert centimeter cube into decimeter cube, and to find the concentration, then you can use this equation to calculate the rate equilibrium rate constant. The reversible reaction and position of equilibrium and equilibrium constant. Again, don't forget also gas equilibria and Kp for gases. They have been giving a question to students in the exam about the Kc, and they haven't asked about Kp for quite a few years. So maybe this year there will be a question about the Kp instead of Kc. Kp is calculated in the exact same way, but now instead of using concentration, we use partial pressures. So it's the product of the partial pressure of the products, each raised to the power of the number of their moles over the product of the partial pressure of the reactants, again raised to the power of their moles. They will give you the moles. They could give you the moles, for example, of one gas, the initial mole of that gas, and ask you to do the calculation to calculate the partial pressure. So you need to know that you can calculate the partial pressure of any gas by calculating the mole fraction. And the mole fraction of any gas will equal the number of moles of the gas at equilibrium divided by the total number of moles of all gases in the mixture. So if in the same way as we calculated the number of moles in the reaction in the previous example, we can do that for the gases as well, and to calculate the mole fraction of the gas. So partial pressure of the gas will equal its mole fraction times the total pressure if they provide you with the total pressure. Remember that the temperature will affect the value of Kp and also of Kc. However, pressure does not affect Kp. The pressure on one side will increase, the other side decreases at the same rate. So you're going to find that the Kp is not affected by the pressure, but it's affected by the temperature. So one of the very common topics that will feature in your exam is the rate of reaction and calculation of the order of the reaction in relation to the different reactant. So first of all, let's go through the Maxwell-Boltzmann distribution. So Maxwell-Boltzmann distribution is the shows you the number of molecule, the energy of the different molecules during the reaction. So the molecules, not all the molecules have the same energy. Some of them have higher energy, some of them have lower energy. So it's the number of molecules over the energy. And then the part at the far right is the will be the activation energy. As you can see, that's a small fraction of the particles will have enough energy for the reaction to take part in the reaction, or will have energy higher than the activation energy. So the different factors that affect the Maxwell-Boltzmann distribution is quite common in the exam. Last year, they asked about the effect of the increased temperature. So remember that when the temperature increase, the curve become a bit flattened, and then it's more skewed to the right, which means that more of the particles or more of the molecules will have energy higher than the activation energy. Probably this year, if this comes up in your exam, they're going to ask you about the effect of the use of a catalyst. When you use a catalyst, the Maxwell-Boltzmann distribution curve will remain exactly the same, because the use of catalyst does not affect the energy of the particles. But what it does is that it lowers the activation energy. So now the activation energy becomes a bit to the left, which means we have more particles now with activation with energy higher than the activation energy. This is why the catalyst would speed up the reaction. And then finally, the effect of increasing concentration and how increasing concentration will increase the rate of the reaction. As you can see, this is the initial concentration. And when we increase the concentration, because we're going to have a higher number of particles now, so the curve will go higher until it reaches the end. Now, the activation energy doesn't change, but now we have more particles which have energy higher than the activation energy, and this is why increasing concentration will increase the rate of the reaction. So calculation of the order. So remember that when we talk about the rate constant and the order of the reaction, remember that we can have either zero order, first order, or second order. So zero order means the rate of the reaction doesn't change if the concentration of that particular reactant changes. So you're going to have a straight line for the concentration of the reactant versus the the concentration of the reactant versus the time. So it's going to be like a straight line like this because the gradient is going to be the same. So whatever the concentration of the reactant when it changes, the rate will always stays the same. So this is the order. First order, you're going to find that the rate is directly proportional to the concentration. And second order means that the rate is directly proportional to the square of the concentration of that particular reaction. How to calculate the order from the data given to you in the question. So first of all, they will keep all the concentrations of the reactants the same, and only one reactant concentration will change. And then if you notice that the rate of the reaction doesn't change with the change of the concentration of that reactant, then this is a zero order. And if the change is exactly the same, meaning when the reactant concentration doubled, you can see that the rate of the reaction doubled as well. Or when there is a zero point 0.6 increase or decrease in the concentration of that particular reactant that affected the rate with the same ratio 0 0.6, then that means it's first order. But if the concentration changes by a factor of x, causes a change in the rate by a factor of x squared, means that this is a second order. So x or the factor that the concentration changes with can be calculated as the new concentration divided by the original concentration. Remember that the rate determining step for any reaction is the step that has all the reactants that affect the rate. So if you find one of the steps has all the reactants that have either first or second order, then this is the rate determining step. If you have only one of these, then it's not the rate determining step. So let's practice how to do this calculation because they would give you a table and ask you to calculate the rate with the changing concentrations of the reactant. So we have now the rate equals K times X squared times Y. X and Y are two reactants in your equation. That means it's second order for the X and it's first order for the Y. And then if they give you the concentration of X and Y, both of them 0.1 and the rate was 4.5. Then if the reactant number 1 changes to 0.15 and reactant 2 kept the same 0.1, you find you need to calculate the rate for this reaction. We know that it's second order for the X, which means that the change in the rate will be multiplied by this factor squared. So now when you divide 0.15 over 0.1, that's a change in the factor by 1.5. So the rate now will be 4.5 times 1.5 squared. So now if both of them changes, so now if we have reactant 1 changed from 0.1 into 0.03, the change now, that means the concentration of reactant X changed by a factor of 0.3, and the reactant 2 has increased from 0.1 into 0.2, so it's changed by a factor of 2. Now we have the original rate, this is the original rate, and then we multiply this by 2 because this is the first order in relation to y. So you first multiply it by 2 and this changed by a factor of 2. So you multiply it by the same factor. And then you multiply it by the square of the change of the factor of the one which has the second order. So this is 0.3, so we multiply it as well by 0.3 squared. This is how you find the rate with the changing concentration. Remember the shape of the different graphs, the concentration time graph and the rate concentration graphs for zero first and second order. For zero order, as we said, concentration time is going to be straight line. So which means that the rate over the concentration is going to be just this flat line here. So no change in the rate. This is zero order. First order, there will be a change in the rate with the change in the concentration, but the change in the rate is going to be directly proportional. So it's a straight line for the rate against the concentration. Second order, we're going to have a curve as well like this one, but the curve for the rate against the concentration is going to be this curve, which means that the rate is directly proportional to the square of the concentration. Enthalpy change, calorimetry, and Hess's law. All of these came in last year exam. However, it's very important as well to remember at least the basic principle. So if they show up in your exam, you don't need to panic and you can answer the question. So remember that for the calorimetry, that Q equals mc delta T, Q is the energy transferred, and then M is the mass of the solution, C is the heat of the specific heat capacity of water, which is going to be provided to you in the exam, and delta T is just the temperature change. Remember that the value of Q that is given that you will calculate in this equation is going to be in joule, and you need to calculate the delta H. You need to change this into kilojoule. So kilojoule, the value of Q divided by the number of moles that caused the temperature change will give you the delta H for that particular reaction. Remember that enthalpy change will equal the total energy gained to break all reactant bonds minus the total energy lost to form all product bonds. Remember that breaking bonds will need to supply energy, and then formation of bonds will release energy. If they ask you this question in the exam, they're going to provide you the mean bond energy of all of the bonds. You just need to calculate the total energy needed to break the bonds for the reactants minus the total energy released when the product is formed. And of course, it's going to be a negative value if it's an exothermic reaction, and it's going to be positive value if it's going to be an endothermic reaction. And then remember Hess's law, the total enthalpy change is independent of the pathway. So you just need to construct your triangle for the reaction and look at the pathways. So now if we have these two these two are in the same directions, two arrows in the same direction, which means that these two are one pathway. So this is pathway one. And this arrow goes in the opposite direction, so that means it's pathway two. The total of the enthalpy change of pathway 1 will equal the pathway total of pathway 2. Now we have pathway 1, let's say this is delta H1, this is delta H2, and this is delta H3. So, and they want you to calculate delta H1, so that means that delta H1 plus delta H2, which is pathway 1, will equal the delta H3. So delta H1 will equal delta H3 minus delta H2. Of course, they're gonna provide you with the enthalpy change of all of the products or of all of the compounds in this particular reaction or in that pathway. Shapes of molecules, this is common in the exam. They probably will ask you to draw one shape of one of the molecules. So just remember that the shape of any molecule will depend on the number of bonds, the number of lone pairs of electrons. The main ideas here is to keep the electrons as far away from each other as possible in space because of the repulsion between the electrons. The repulsive forces between the lone pair and lone pair will be bigger than the repulsive forces between lone pair and bonded pairs, which is more than the bonded pairs with bonded pairs. And that affects the shape of the molecules and the angle as well. So let's have a look. So if we have just two bonds here with no lone pair, then the shape is going to be linear because the maximum they can be away from each other in space is 180-degree, basically opposite direction. If you have three bonds um, uh, with no lone pair, then it's going to be trigonal planar. The angle here is 120. And then if you have two bonds and two lone pairs, for example, like water, then it's going to be pent. These two lone pairs have pushed the bonds towards each other a bit because they have more repulsive forces in between them. And then if you have something that has three bonds and one lone pair, something like ammonia, for example, then it's going to be pyramidal. And remember that, or have a look at the angle here. You're going to find that the angle here is 107 is bigger than the angle in case of water. This is because the repulsive forces between the two lone pairs is bigger than the repulsive forces between the lone pair and the bonded atoms. Now, if we have four bonds, no lone pair, something like methane or like ammonium ion, for example, this is going to be tetrahedral. The bond avidity is 109.5. Again, this is bigger than the three bonds, one lone pair, and bigger than two bonds, two lone pairs. If you have five bonds, no lone pair, it's going to be trigonal bipyramidal. And if you have six bonds, you're going to have it as octahedral with a bond angle of 90. If you have three bonds and two lone pairs, it's going to be T-shaped. If you have four bonds and one lone pair, it's going to be seesaw. And if you have four bonds and two lone pair, it's going to be square planar. So you need to look at the how many bonds are there and how many lone pairs, and to find the shape of your molecule. Please remember the dative covalent bond is at the bond when both electrons come from the same atom, like in ammonium. So you have the 3NH, and then you have the ammonium atom where the two lone pairs of electrons from the nitrogen are the source of the bond. This is called dative covalent bond. Remember that electronegative atoms like fluoride, chloride, and bromide, they will all increase the reactivity of the acid, as they are electron withdrawing groups. They have a negative inductive effect, so they will pull the electrons toward themselves, and they're going to weaken the OH bond. Remember that the strengths of the bonds come in that order. Covalent bonds have the highest strength, followed by the ionic bonding, then hydrogen bonding, and then the permanent dipole-dipole forces, which we can find in polar molecules, and then finally the van der Waals forces, which can be found in any molecule, whether it's polar or non-polar. Remember that hydrogen bonding is formed between the hydrogen on nitrogen or oxygen only, so you must have an NH or OH for hydrogen bonding to take place, and you with a lone pair of electrons on another nitrogen or oxygen. The other nitrogen or oxygen doesn't have to have a hydrogen atom. It can be like a carbonyl group like this one. So you're going to have hydrogen bonding between this hydrogen and this lone pair, and it's drawn as dots like this. This is called hydrogen bonding. The math skill in the exam paper. This exam paper is math heavy. So remember the ideal gas law or ideal gas equation. PV equals nRT. P is the pressure in Pascal. V is the volume in meter squared. It's not in centimeter squared or decimeter squared. So if they provide you the volume, or if they give you the volume in decimeter squared, you have to divide this by 1,000. If they give it to you in centimeter, cubed, you have to divide by 10 to the power 6. And at the number of moles of the gas, R at the gas constant, which is going to be given to you in the exam, and T at the temperature in Kelvin, not in Celsius. Remember these two triangles for the calculation of the number of moles from the mass and molecular mass, and remember how to calculate the moles or the concentration if you have concentration, volumes, and number of moles. Remember that the percentage yield is the mass of the product that is actually made over the maximum of the theoretical mass of the products times 100. And remember that if they ask you to calculate the uncertainty, remember the uncertainty